Hi, so this is the recording for the course project. Um, so I'll start with a tool choice, a quick intro, and then I'll jump into the modeling approaches and the model building, the model evaluation, and the interpretation. Tool choice, I picked Python because it gives better control and also it's better for nonlinear algorithms. Excel is easy for simple linear, so I picked Python for this. Coming to the model approach, I first understood the problem. This is a regression problem. The P is continuous, and there are four features, out of which I predicted ambient temperature to be the most important feature because it had the highest correlation. I'll show you that in a bit. For metrics, I chose the RMSE. It's the same unit as the target, which is in megawatt, so it is directly interpretable, and it approximately penalizes large misses more heavily, right? Which matters in this problem statement. Um, to quickly, the correlation table, as I was saying, I figured that the ambient temperature is the most important. And coming to the algorithm, I picked two linear algorithms and then two nonlinear. For linear, I picked the linear regression and the polynomial regression. And for the nonlinear algorithms, I picked random forest and gradient boosting. So I'll give you the comparison for these models. And as you can see here, um, the RMSE value for the linear regression turns out to be like close to ANOVA 4.5, 4.2. And as you can see, the random forest has the lowest, which is 3.45. And for the cross validation, I did like fivefold, and I did the 80-20 split, which is which is a standard and a strong split. And of course, the reason to use cross validation and split is to reduce the bias as much as possible. Let's quickly move on to the model evaluation. So here I have a Python script that I am running right now, and it shows you the model results, the model performance included. So as you can see, the RMSE value here is 3.23 megawatt, the MA is 2.31 megawatt. The R square, which is the key factor for the interpretation, the R square is 0.964. So as we interpret, the model achieves 96.4% R square, meaning it explains almost all the variance in the power output, and the typical predictions, within about like 3 megawatt. Now I will quickly show you the other two graphs here. One is the prediction versus the actual, and then the other one is the residual. As you can see, in the prediction versus actual here, um, the cluster is tightly, like around the prediction line, which is the red line. And in case of the residual, as you can see, the clusters are, or the residuals are pretty scattered. There's no pattern as such. What this means is, the model isn't biased symmetrically anywhere. So to quickly summarize, I chose random forest because it had the lowest, most stable cross-validation error. It captures the nonlinear structure of the data, and I also looked at the computation cost of this random forest, and it turned out to be not much. So overall, random forest turned out to be the best algorithm for this. Thanks for watching.